1, 2, 3.
You're talking about you record that, so everybody just go online and look at it.
Yes.
Okay, good. I like that.
Okay. We are recording now finally. Here we go. So it'll be streamed on YouTube later. Okay. Well, let's begin. You've read the chapters, and let's talk about PLC. Do you know what PLC stands for? No. PLC stands for Progressive Learning Curve, which means, I'm kidding, that's what it stands for. Progressive Learning Curve basically means that you always learn about PLCs. They're always changing, the hardware's changing, everything's changing, so it will never be constant. We're going to teach you the fundamentals in this class, but it's kind of up to you to keep up with the technology as it progresses, naturally. Just like between smartphones and iPhones and Androids, it's always changing. So, okay. So, programmable controllers pretty much are everywhere in industry, and basically a PLC is a small computer that runs a program that you make, and basically it makes decisions on the input, the I/O, and those decisions the result is an output, or the output to the I/O. Okay, so basically inputs happen, we examine the inputs, and then from there we make a decision and turn on an output. Pretty simple, right? Yep. Okay, so initially the PLC, it was used to replace relay logic, but it has a lot more functions than that now. It can do data collection, all kinds of good stuff. And it's basically same principle as those complied in computer architecture, okay? So, now you stop me if you have any questions as we go through here.
What is the comparing?
Well, basically what we're doing here is we're comparing, that's a small PLC on the left, and that's a laptop on the right. They're just, you know, a PLC is just a small computer, is all that's saying. One of the advantages of having a PLC is the old way was this on the left, the relay control panel. And this is a small, used to, panels would be 10 foot long and would contain thousands of these relays for a very complicated machine. So you can imagine how much trouble it was to troubleshoot that much relay logic. You had to, all of these relays, right here, will fit in the small box on the right at the top corner, the gray PLC right there. So that's what it replaces. Now there's a motor contactor and some I/O below there that's separate, but basically what they're saying is all the picture on the left is replaced by the small gray box on the right. So that's quite a huge space savings, plus it's much easier to troubleshoot. Okay? Well, and troubleshooting is, you go online with them and you see the problem visually instead of trying to figure it out with a meter. Does that make sense? You can see the whole picture instead of just what your meter's showing you at that point. That's the major advantage of a PLC. Increased reliability. Using a PLC, I like to use the term softwire. That's your program, because when you have wires and devices running out there, they're bound to fail. And when you have the PLC, you eliminate a lot of that wiring, which means it's not going to short out, it's not going to get corroded. It's all done inside the PLC. So to give you an example, I redid a machine one time, a German milling machine, and it was all hardwired. Well, it had a 5-inch conduit going to the machine stuffed full of wires. There might have been 300 wires in there because there was quite a few limit switches and safety switches. Well, it was replaced with a PLC, and instead of running all those wires, we run a single small blue hose, one wire, to communication modules mounted throughout the machine, and we eliminated all that wiring that was giving us problems in that machine. We basically, the control panel was separate from the machine, and what we did is we eliminated 90% of the wiring on the machine with one blue hose in a PLC program. Does that make sense? So we went from we didn't take the conduit out. We went from a 5-inch flex conduit full of wires to a 5-inch flex conduit full of a couple of power wires, an e-stop, and one blue hose. So we went from a bundle of wires that big to a bundle of wires that big. So that's the reason we use PLCs. So they're not mystical, they're not magical. Anybody can read a PLC program. They're not that hard. More flexibility. Well, let me tell you something. A PLC you can rewire on the fly. And what I mean by that is you can change the program while they're running if you're careful, and change how things work. So let's just say that we had a photo eye on a line, and we can use markers even though that won't go online. That's okay. So we have a conveyor system that's running product, right? And we have a little photo eye right here, and let's just call it photo eye 1. And when this photo eye is made with a box, it stops the line, right? Yes. Okay. Well, so let's say we have another conveyor over here with photo eye 2 ahead of it. Well, if this was hardwired, we would have to switch the wires, wouldn't we, to stop the box when it stopped this conveyor right here. Well, if it's on a PLC, we simply change the program, and now this conveyor will stop when there is a box here instead of when there is a box there.
So you say that you can stop the...
If all your devices are hooked to a PLC, the only limit to what you do with it is your program, which means any combination that you want to do, if it's hooked to a PLC, you can change it to make it happen.
So why it's still running?
And why it's still running, yes. Now, I don't guarantee there won't be a mess after you hit accept, but you can do it. There's some safety concerns and different things in there you have to watch out for, but it is possible. So, let's go on to the next one. Low cost. Well, let me tell you something about PLCs now. You can buy a Rockwell programmable relay for $80 that has 4 outputs and 4 inputs, and it's $80, and the software is free. And there are other brands. Well, if you went and bought an Allen Bradley relay base, one of these relay bases, that would be $80. So basically, it is a quarter or a fifth the price of buying 4 of these, right? All these wires and relays would cost more than a small little PLC. You with me so far? Yeah. So it's really a lot cost. One of the main things is, you know how much copper costs now? We get rid of a lot of copper when we run a PLC. Communications. We can talk to other PLCs in the plant. Instead of running control wiring, we can transmit data, we can log data. We can even put it online for people, and I've done it where corporate could go to the local plants and look at production data in real time. And that's done with software packages and PLC. But somebody across anywhere in the world can log in and look at production in real time. So that's kind of Big Brother watching you.
What do you mean by real time on the PLC? What do they mean by that?
Real time means, well, when I say real time, that means as it's happening. As production's going on, there'll be a slight lag, but you can pretty much see what's going on as it happens. If a photo eye blocks a box, then it's immediately, you can see that. That help?
Yep.
Okay.
I tried to read all the stuff, but I don't get it.
That's okay. There was a lot to absorb, but we're just going a general overview, so we'll finish going through here and see how you do. All right. Okay. Here is an example of, we're talking about some sensors. Well, machines that process thousands of times per second an object that spend only a fraction of a second in front of a sensor, they have to have a PLC in front of them. Because if we had an old relay, well, a relay is mechanical, right? There's travel time between those contacts. Well, we can detect stuff and act on it using semiconductors through the PLC much faster than we could the old way with the relay. Does that make sense? The action time is not even in comparison. You can even look that up. You ever look at they have like you can order a relay, and you can order the old mechanical relay, or you can order a semiconductor relay. And if you'll go dig down in the specifications, the response time on the semiconductor relay is in microseconds, whereas, anyway, the response time on the old relay is maybe half a second, whereas on the semiconductor relay, it's like a tenth a second. Does that make sense? There's no comparison. Plus, when you don't have the mechanical actuation, it lasts quite a bit longer. Semiconductors last a lot longer than mechanical, for the most part. It depends on your environment, too. Lightning and stuff, that'll take them out. They're not as resilient to power surges unless you install power surge protection. Okay, easier to troubleshoot. Here's an example. To find and fix problems, users can display the control program. So basically, instead of going out there, you can pull it up on the computer and you can see that, well, we can monitor in real time what's going on and why the product's not flowing. Does that make sense? Much easier. Okay, let's talk about parts of a PLC. All right? Well, the major parts of the PLC is the CPU, the I/O or input-output section, power supply, and the programming device. Example, your laptop. Okay. Let's walk in here. I should still reach in here. May cut off a little bit, but that's okay. Power supply, processor, I/O. All right, and then all the I/O fits into a rack. That's the old PLC. Yeah, that's the last generation, which is what we're going to train on. It's still in use. The next generation is control logic, and this is an example of a package controller, and you'll see that it is the power supply is built in, the I/O is built in, but it has an expansion module. So this whole thing, this box right here, is the same as that big box up there. Does that make sense? Newer.
So sometimes just get the power supply built inside the line.
Yes.
Okay.
Built inside. This one actually runs on 24 volts, but you can get them there.
Okay. You
just hook it up. So we don't. The bad thing is if one part blows up, you throw the whole thing away. Okay. The good news is this whole box here is cheaper. It's about a fifth the cost of that box out there.
Is this what they call the fixed type?
Yes, they call a shoebox. You ever heard the term shoebox? Well, they'll sometimes, just like you put your shoes in a shoebox. That's because everything's built in. You can get modular, but this is the new style. All right. All right. So we'll go on, and let's kind of look at this a little closer.
So I got a question about that one. How did they, is the CPU read from the input first and then go to the memory and then go back
Okay. It's a little different in the new one, but in the SLC 500, first, it scans the inputs, okay, and those inputs go into what's called the input data table. All right? And from the input data table, which is just a binary storage location, it goes through the program. When the program finishes scanning, it updates the output table. Once the output table is updated, it sends that information out to the real world, to the card. Okay? So that all happens really fast, milliseconds. But that's what it does, is power supply simply powers everything. Inputs are read. It is easier to say it reads the inputs, it processes them, it runs the programs on the inputs, and then updates the outputs once the program is scanned. We're going to get into scan time in a little bit. Okay. Now, sometimes you hear the term architecture, and architecture basically refers to everything in your PLC system. Open architecture allows the system to be connected to other devices and manufacturers. Now, when you're talking Allen Bradley, they are going to an open architecture system, but the old stuff was pretty much, if it wasn't Allen Bradley, it wasn't going to talk to the SLC very easily. SLC, or SLC for short, is just the product model. The gray box I showed you in there, that's the last generation. Okay. Control logic is the new generation. Now we're going to be training on the last generation, which is still applicable. They still make them. Closed architecture is Allen Bradley. You have to buy Allen Bradley stuff to work on an Allen Bradley PLC. That's kind of a closed architecture scenario. They're going open architecture because everybody else is doing that. So anymore, you can buy a Allen Bradley PLC, and you can buy third-party I/O cards that work with it over Ethernet. So you don't have to buy entirely Allen Bradley anymore. They've started integrating. You can buy Allen Bradley PLC and remote into a ABB drive and work with it. They're not locking everybody down into just buying Allen Bradley. Now, for setup, if you buy the Allen Bradley stuff, it sets up much easier on the Allen Bradley PLC. Okay, but it's not necessary. Now, what we showed you on that packaged CLX controller I showed you is a fixed I/O system. Okay, and when it says fixed I/O, that's what sometimes referred to as a shoebox PLC. It basically means that the I/O and communication is built onto the PLC. If you burn out something, you have to move the wire, you have to change the program, or you throw it away and get a new one. There's no fixing it. Okay, it's fixed I/O. Now, modular I/O, which is what we looked at in there with the gray SLC boxes, you'll see a rack. Okay, and within each one of these racks, a card goes. You can stay there. I'll be right back. Slot 1 in a slot 0 in a SLC always takes the processor, and then the preceding slots take whatever kind of I/O cards you want. You want inputs, outputs, counters, different things. Okay? So, yes. Now,
so you can swap it to any slot,
yes, if you change the program. The processor must remain in slot 0. It's just one of the rules. Yeah, in a SLC system. The new ones, it doesn't matter, but in the old ones, the old gray ones, the SLC, it does. It has to go in slot 0. So, power supply. What people don't seem to realize is if you're talking digital electronics, you're talking DC power. Even if you hook AC power to it, it's changing that over to DC because the point of digital electronics is usually a 5-volt circuit, right? Somewhere it all gets down to 5 volts, and then it changes back to 24 or 120 AC, whatever it is. But so normally in these small PLCs, the power supply is built in, just like it's shown here. The CPU, you're holding one in your hand. It consists of a microprocessor, and all it does is implement the code. That's the brain, is all that is. You can even look on here if you wanted to look close here. Here's options for expandable memory. If you want to, on this one has expandable memory. You could buy a chip and plug in there. And there's a processor. I don't know exactly. I think that's memory, and I think that's the processor right there. I don't swear to that. Now, we're going to talk about scan time. So the PLC program is executed as part of a repetitive process called a scan, okay? And it starts with reading the inputs, execute the program, diagnostics and communications, and then it updates the output, okay? We sometimes forget about diagnostics and communications, but basically read the inputs, execute the program, update the outputs. Now, the I/O system, remember that's how we get information. The only way we get information into a PLC is through the inputs. That's all it knows for the most part, unless you do messaging. But for the most part, it's the inputs, and those are anything you can hook to it. Push buttons, limit switches, proxies, temperature sensors, any kind of sensor you can imagine, there's a way to hook it to a PLC. That makes sense? And here's a typical diagram showing how they go in there. So, okay, output devices, such as a contactor to start a motor, a solenoid to open a water valve, a light to signal something, a bell, a whistle, anything that's an output. So any of those instances are output. One thing about outputs on a PLC is those little cards have an amp rating. So you must make sure that, like you see on the left, it shows a big NEMA style contactor. On most small PLCs, that big contactor would pull too much current. It would work for a little while, but it would eventually burn up. So you have to pay attention. The outputs on these PLCs, they don't handle a lot. You can buy them that handle more. Most people put a relay on it if it has to handle high current. But anyway, so there's an output example of output. Pretty good so far? Yes. All right. A programming device. The one on the left is a handheld programming device. We're not going to talk about that because, as far as I'm concerned, they're gone. All right, we're going to talk about the software, the RS Logix 500 software. That's what we're going to talk about. I've used the handheld programmers, and not by choice, because they're really difficult and confusing. So we're only going to talk about the ladder logic, the RS Logix 500 software. And it just says it runs on a personal computer. We knew that. Now, a program is a series of instructions that direct the PLC to execute action. So this is an example of ladder logic. The reason we have ladder logic is because it's very similar to what's called a line diagram that's been around forever, 100 years. Sometimes we'll say it's been around for 200 years. Well, I haven't been around that long. It's been around for 100 years, and what it is basically a logic diagram. For used to, when you had we talked about relay logic, they all had to have line diagrams, and people would have to interpret those logic diagrams. Well, in order to facilitate all these old school electricians, in order to get them to program the PLC, they designed the software to look just like the logic diagrams they were used to writing and working on. So instead of working in paper, they work on the computer or the program. That makes sense? So it's pretty simple. It comes with instructions and outputs. All right? Inputs on the left, outputs on the right. And those are the rules for RSLogix 500. Now be aware that control logics, you can cheat. We're not going to talk about that. But it changes with software versions. They've modified it. You can cheat a little bit. But when we talk RSLogix 500, the gray one, inputs on the left, outputs on the right. We're going to go into ladder logic just to give you a quick example. This would be say, the instruction on the left would be a switch. So it would say if switch A is on, and then the next one would say if switch B is not on, say it's normally closed, then turn on output C. Pretty simple. So if light switch is on one side of the room, the light switch is off on the other side of the room, we're going to turn the light on in the room. So you have to, you know, their logic is either, this is binary, so we're either on or off. And we have either, you know, we either have examine if on or examine if off. So it either works, if it has a 1, it's true. If it has a 1, it's false. Depends on how you program it. Does that make sense? In this instance, the first one, normally open instruction, if it has a 1 in that data table, it's true. The other instruction, if it has a 1 in that data table, it's false. It evaluates it as false. But you'll get that pretty quick. So kind of jumping ahead of ourselves. So principles of operation. All right. So let's go into this one. And all right. Here's an example of a mixer process control. So we have a motor, and it automatically starts to stir liquid in this vat when the temperature and pressure reaches a preset value. It has a manual override button, which means it just turns the motor on. Okay. So let's look at this example. Here we have L1 and L2. I'll tell you what, though. Let's take a break right now, if you don't care.
I'm slow learning.
What do you want to put up there? Okay, we're back. So what we have here is excuse me, pressure temperature switch, and how this works is when the pressure switch is activated, and the water is at a certain temperature, we're going to turn the motor on. Okay? And the motor is going to agitate this tank like a washing machine, right? Alternatively, we can hit the manual push button and we will bypass. You see how electricity would flow through here, here, and then turn on this? We can bypass that by turning on this manual push button, going around, and then going to the motor. Does that make sense? Okay. So let's look at a PLC method. This was hardwired. This is the old way. Let's look at the new way. Here, instead of wiring everything to its device, we simply take everything to an input. So we take a pressure switch, it goes to an input. Temperature switch, it goes to an input. Manual push button, it goes to the input, right? With me so far?
Yes.
All right. And the output, we simply take the output and go to the motor. All right, and that's tied to the output module. This one goes to an input module. That one goes to an output module. All right, so let's look at the ladder logic. They look very similar. Here's a normally open switch. It's simply called pressure. Here's a normally open switch called temperature. It turns on the output, which looks like a coil. Or we can bypass everything with a manual push button. So let's go back and review. Normally open switch, The only difference being that between the program and the schematic is, you know, we have schematic symbols. Well, in the program, they're all the same. We simply label them. So look here, normally open, motor comes on. Normally open, push button, bypasses everything, motor comes on. Over here, same deal. Just got labels. So that's the whole premise of ladder logic. Okay? So if you can read line diagrams, you can read ladder logic. They read just like a book, left to right, top to bottom. Okay, for the program to operate, the controller is placed into the run mode. Okay? Now, PLCs usually have 3 modes. They either have a program, you're writing the code, a run, or most of them have what's called a remote, which means that remotely, with the software, you can change it to run or program. It's remotely controlled. Or you have a little key switch that says you're either run or not. This one doesn't have that. Some of them have key switches. This one has a small selector switch right here. See, it says run remote program. So it has a small selector switch that we can change. Okay. So during each scan, the PLC, it looks at the the status of the inputs, devices, etc., executes the program, and changes the output accordingly. The coil 01, it's turned on when contacts input I or input 1 and input 2 are on, then we're going to turn on output 1. Right? And if any of these conditions are false, it doesn't happen. Here's the actual ladder program. Right here. That's what it would look like in the software. Very similar. You've seen RS Logix 500 software before, have you? Okay. Yeah.
I don't know. I did it before.
All right. So here is a small. This is actually called a programmable relay. These are going away. The ones I told you about coming out that are $80 are taking their place. They're much easier to use. This is kind of another wiring diagram for it. You follow that? Here's electricity coming in to L1. Here's the neutral wire to L2. Neutral wire is tied to the starter also. We have electricity going through the pressure switch. And when the pressure is at a certain point, it closes and it goes to input 1. Temperature is at the right place and it goes to input 2, or we have a push button and it's tied to input 3. And then of course only one output, and that's the motor starter. And everything else is contained inside. See, here's a little program right here.
So on the Q1, you actually have power to that one. Am I correct? Q1?
L1?
The L1?
Yeah, L1 is coming in here, and this is a fuse, symbol for a fuse, and they're jumping the same power to go off to everything else. You see the jump?
How about the output on the Q1?
See here, this is the power coming down through here. This is a relay built into the PLC. That's inside the PLC.
Okay.
So it has, each one of these has power in, and then when the PLC tells it to, it's going to see the little switch, it's going to close that and send it out. Yeah, that's what that is.
Okay.
That's kind of showing the wiring diagram also. So. Modifying the operation. Exciting stuff. Okay. One of the main things we talked about is how easy it is to change. All right? If we had a relay system, we'd have to go out there and move wires. We'd have to shut them down. We can do this on the fly. So let's just look at this. That looks just the same. Yeah. Okay, they changed. What have they done different? I don't see what they've done different from the last one.
They moved the thing.
Oh, yes, okay. Yes. Yeah. Yes, thank you. So the last time the manual push button bypassed the temperature switch. Well, if you wanted to make this change, you'd have to go out there and move the wire. Here, we simply change the program, and that's simply as easy as grabbing that parallel branch and dragging it over and then saying, that's the way I want it, and it's done, right? All right. And here's another example. So, PLCs versus computers, all right? So, architecture is basically the same. PLC is just a small computer. The only difference is PLCs are designed to work in a harsh industrial environment. Oil, grease, high humidity, they're kind of battle hardened, as where a PC would not last. And in fact, you can buy industrial grade PCs and laptops to run in the industrial environment. They cost a lot more because they're designed a lot more rugged and have filters and stuff for the air and everything. So properly designed PLCs are not affected by electrical noise like from AC drives or large motors or fluorescent lighting. That what they're saying is a home PC, they're not shielded like a regular PLC from electrical noise, is what they're saying. Unlike the personal computer, whereas languages vary, I don't even know the last count of different programming languages. There's C++, Visual Basic, old Cobalt. You can even program, I don't know what it's called, Android, Java. You have all these programming languages. When we talk PLC, we want it standardized because what we want is for industry, from one maintenance guy to the other, to be able to train and learn just one language. So we use ladder logic. And everybody uses ladder logic. And it's built into its memory, and it's not permanently attached to the keyboard, CD. You can just go in there and take this program out and look at it. That makes sense? I like to compare PLCs. They do one thing really well, really fast, and that's read inputs, execute a program, and turn outputs. They're not, they don't play music, they don't play videos. That's all they do. Read inputs, execute a program, update outputs. That's all they do. So there's a difference. PLC control systems, they've been designed to be easily maintained. Troubleshooting, it's simplified because a lot of times flashing red light means something's bad wrong. If you see a flashing red light on a PLC, something's wrong. If you see a flashing green light, it usually means that something could be wrong, but it's probably more than likely a status or waiting. Solid green light means all is great. And anything red or flashing red on a PLC is bad. Sometimes your I/O comes on with red lights, but if it's on the processor, flashing red light is bad. And most devices. It talks about how if it's a modular system, it's easily replaced. Okay, you don't have to throw the whole thing away. You don't even have to unwire it. The wiring harness comes off the front of those cards. So you take 2 screws off and slide a plug off, and then you simply change the card and put it back in with the old plug. So you don't have to rewire it. You've seen PLCs before, it has a big bundle of wires, but when you change out a card, you don't have to rewire it. You simply take it. It's a quick connect, basically. So, PLC software that was written and run on a personal computer falls into 2 broad categories. So, software that allows the user to program and document or to write the program. is ladder logic. And it also gives you the ability to document your program. So basically, what it's saying here is the PLC program that you have on your personal computer holds documentation, right, to explain what's going on. The PLC program that is held inside the PLC does not. So you have to keep up with both if you want. The PLC program is required to run the PLC. The documentation is filled in on your PC, basically. And sometimes the program's worthless without documentation. It's worthless. It can be so big and convoluted that without documentation, it can basically, and without prints to make your own documentation, it's just not very good. So documentation is very important when you're programming a PLC to keep up with that. Unless, of course, it's something real simple, you can get away with it. Something like here is okay, but we're talking, this can be thousands of lines of code, you know. And if you don't have any, all you have is numbers on it, how do you troubleshoot that? If all you have is I:1/10 50 times in a program, you have no idea what that is, right? So how do you troubleshoot it? You don't. You have to know what that means, and that's where we have descriptions. PLC software that allows the user to monitor, control the process is also called the HMI, or human interface, human machine interface. Touchscreen. You got touchscreens at work? That's HMI. If you have software running on a PC like that lets you modify the PLC or start and stop equipment, that's HMI software. So your PC is now an HMI. Typically, we like HMI touch screens because they're more rugged. People can't try to play solitaire on them. That's a joke. Believe it or not, that some of the Rockwell HMIs, if they know how, the solitaire is on there. They just don't know how to get it. Yeah. Yeah. Some Rockwell computers are actually Windows CE, and they're embedded, and you can get them open where you can open up Excel and stuff on them. But for the most part, they're locked down. It enables the user to view a process or graphical representation of a process on a monitor. So you have a machine, you have a graphical picture of the machine, and you have little red lights that say this is a limit switch, and it's on, and it shows in real time what's going on with the machine so people can troubleshoot it. That makes sense? Okay. PACS, that is just a buzzword. It's a PLC. Programmable automation controllers combine PLC ruggedness with a PLC functionality. So, you know, I've heard the word PAC. It's a PLC. That's what it is. But it's supposed to be the advanced capabilities of a PLC with control, communication, data logging, signal processing with rugged hardware performing motion. Basically, PACs are the new PLC. That up there is actually called a PAC. Yeah, that's actually called a PAC. It's the new buzzword because it has a lot more bells and whistles. And you can even, not that brand, but you can even get PLCs, the touchscreen and the PLC are one device. So you program the PLC and the outputs on the back of the HMI, so it's just one box with a touchscreen and everything sits to the back. PLC size and application. Well, the first thing you need to do before you decide what PLC you're going to use is you need to know how much I/O it can support, right? You don't want to buy a PLC that only supports 100 I/O for a system that's going to use 99 I/O. You know why? Well, you always need to oversize your I/O by about 20% because no matter what you do to a system, it's going to get modified or something's going to get changed. So you never want to push that limit. So if you're going to buy a PLC and it only works with 100 I/O, inputs and outputs, 100 wires go to it, and you need to run 99, well, then you just need to pay the extra money and get the bigger one because eventually you're one wire away from shutting them down. Does that make sense? Eventually it'll expand to the point that somebody will say, well, why don't we add a flashing light over here in a couple of years, or we add a buzzer over here that tells people this, or why don't we put a photo eye there? So you always need to oversize a PLC by about 20% of the I/O. Like I said, it's the most important factor in size. In general, nano is the smallest size, which has about 15 points, followed by the micro, which is 5 to 128 points. That means I/O. When I say I/O, I mean inputs and outputs combined. You got me there? Yeah. So when you hear I/O, that just means inputs and outputs. Medium tops, 128 to 512, and larger tops over 512. So matching the PLC with application is a key factor in the selection process. All right. So, and the reason why, because some of them can get quite expensive, and you don't want to tell somebody halfway through a project, oh, we need to rip all this out and start over and spend another $10,000. It don't go over well. I've seen it happen. It doesn't go over well. So, there are three major types of PLC applications: single-ended, multitask, and control management. Single-ended means the PLC is controlling one process, all right? It's controlling a pump and a motor, what we looked at earlier, all right? A multitask PLC means it's controlling several processes, which means a control logics, like what's pictured right here, it can control two separate systems just fine. You assign I/O to half the plant and the other half the rack to the other half the plant, and it can actually, you see that big rack right there at the top? That actually could have two processors in it. One processor could run one machine and the other processor could run the other machine. They can share I/O. All right? So it's multitasking. It has enough computational power that it can run multiple things at once. Does that make sense? It's like that's a Game Boy. Well, that's probably not. But that, what I showed you up here, the control logics, that's a smartphone. Those in there are Game Boys. You know what a Game Boy is? Those are flip phones. That's an Android. Okay. Does that make sense? Yep, that makes sense. That's one of those old flip phones, and that right there is a top-of-the-line smartphone. So that's a comparison. Control management involves one PLC controlling several others. This is pretty much, I've only done these in data acquisition. Okay. One of the reasons is some people, you can make a PLC run the whole plant, right? But what happens when that PLC goes out? The whole plant's gone. So what this is typically, when it says control management, this is data collection to show you production values or alarms or anything on a central screen. So basically the PLC just communicates with everything and it doesn't control everything, but it monitors everything. Does that make sense? All right. Memory. Memory size is usually expressed in K values, 1K, 6K, so forth and so on. We will use the measurement kilo, abbreviated K normally. It refers to 1,000 units. So when dealing with computer PLC memory, however, 1K actually means 1,024 because this measurement is based on the binary number system. So basically, that's the number you end up with. The maximum number in binary is 1024. We're not getting into binary yet, so don't worry about that. I don't even want you to think about that right now, okay? Don't think about that.
I have 500 today.
That's okay. Don't think about it yet. We're getting to it. Okay. Hold all your binary questions till later on. But basically, this is kind of laying it out. You have a home computer, okay? How many megabytes of memory do you have in it?
4 gig.
You got 4 gig. How big's your, well, How many megabytes are in a gig? 1,000.
1,000 megabytes.
Yeah. Okay. Well, you know how many a K is? 1,000. I think 1,000 K is 1 megabyte. Or no?
No, 1 gigabyte.
No. We're talking K. This is because the memories are so small. It's actually maybe it's 1 million. Anyway, I think it's 1,000 K is 1 megabyte, or is it? It might be 1,000,000 K is 1 megabyte.
1 K equals 1,000 K for 1 megabyte.
Yes.
1,000 megabyte equals
1 gigabyte.
1 gigabyte.
Yeah. So that's where that's going. Memory, you can run out of memory in the old ones. These right here, they add so much. You used to have to worry about that, but now they put megabytes, and you know some of the control they come standard with 32 megabytes. That doesn't sound like a lot, but when we're talking ladder logic, that is a massive amount of code that you can put in there. Because these programs don't take up much room. Okay, the one you had in your hand was probably 512K. That holds as much as one of the old floppy disks, the big ones.
Yeah, the big old time.
They had a big 5-inch when they were floppy. So, yeah, here's a layout. I just showed that. There's the microprocessor. Here's expandable memory. Here's some integrated circuits and battery backup. So the amount of memory it needs depends on the amount of I/O points, right? The amount of memory it needs depends on the amount of I/O points and what it's going to do with them. All right. Size of the program, whether it's going to collect data and store it. Number one key here is future expansion. It costs a lot of money to upgrade, so you might as well spend a little extra to make it as big as you possibly think you're going to need to start with. Because if you don't, you're going to end up spinning it anyway, right? If you bought a small package controller to do a little thing and they wanted to add to it, and you said, well, we can't do that, you're going to have to spend another $10,000. You should have spent $10,000 to start with, and you could have saved the $5,000 you spent on the smaller one. Does that make sense? Yeah. So, instruction set for a PLC is the different types of instructions supported. We have examine if on, examine if off, output energize, output latch, output unlatch, TOF, timer on, count up and count down. So we're going to get into those here in a second, but I just wanted to show those to you. You'll have to memorize those. So they're not too hard. Oh, are we done? I think we are. You have to know what that means. Yeah. So let me stop this recording. We are done, I believe, with chapter 1.